Okay, section 6.9. We are now ready to begin talking about the family of complex numbers. Now that we introduced you to imaginary numbers, we can expand that just a bit and talk about complex numbers. So, looking ahead, complex numbers, if we talk about, let's down this down. Complex numbers is a number in the form a plus bi, where before we were discussing it has to be a number with a bi in it. Now we're talking about a plus bi, where a and b are real numbers and the I is equal to that square root of -1. A is considered the real part and the b is the imaginary part if you look at the statement. So A goes with that A, and the B goes with this part that represents the imaginary part. Two complex numbers are equal if A plus BI equals C plus DI, which really means that the real part A has to be equivalent to the real part C. And the imaginary part BI must be equivalent to DI. Now that does not mean they have to be the exact same number, but as long as their values are equivalent. An example of that would be if A was 6 and C was 12 over 2. When you reduce that 12 over 2, you do get the 6. So they don't have to look identical, but their values must be identical. And then, last but not least, in the set of complex numbers, you will perform all addition, subtraction, multiplication very similarly using the same postulates and rules that we used with real numbers. The only exception there is the inequalities. We won't be doing less than, greater than with complex numbers. Okay, so moving forward, let's try some good old addition, subtraction, multiplication of numbers, and let's highlight them. So let's start here with the supposedly easier stuff. If we have addition of complex numbers, which is this first example, we can look at it and say, well, wait a minute. I have the complex number 6 minus 5i, and I want to add that to 3 plus 4i. In order to do that, the rule is add the real part with the real part, the imaginary part with the imaginary part, including looking at the signs. So here we would go. 6 plus 3 is 9. A negative 5i added to a 4i is a negative 1i. If you choose to write it as 9 minus I, that would be equivalent. You don't have to have that 1 there to hold a place value or anything. Okay, so addition. Reals plus reals, imaginaries plus imaginaries. Next, let's try the substitution. Same way, if we have a 2 plus I for our complex number and a 7 minus 2i for the other complex number, and we're subtracting them, the rule would be real minus real, imaginary minus imaginary. So it's sort of like terms when we were doing variables. Very similar. So 2 subtract 7 is negative 5. I subtract negative 2i, or think of it as 1i minus a negative 2i. Minus a negative is the same as plus a positive, so 1 plus 2 is 3i. And we like to keep things in the form a plus bi, which means the real part will be first and the imaginary will be the second part. That's just a standard look for all complex numbers. All right, secondly, we have some multiplication that we can do. But I want you to look at these multiplication types here because they are definitely different. On the first one, 3i out front is like an imaginary number. It doesn't have the real part in front of it. If it did, that real part would have to be a 0. So we're looking really at 3i. It looks like a monomial. Inside the parenthesis is the number 12 minus 3i, which is the complex number. So if we have a mono times a bi, think about, we would normally, if these weren't imaginary numbers, do distributing. And that's exactly what you need to do, and then simplify from there. So with me, ready? 3i times 12 is 36i. Think of that I right now just like you would any other variable. 3i times a negative 3i is negative 9i squared. Now let's simplify what we can. Again, we want to try to end up with a plus bi form. So 36i, not much we can do with that. Minus 9i squared. I squared is better known as negative 1. So that'd be negative 1 times a negative 9, which is a 9. Let's rewrite this. 9 plus 36i when we simplify. 9 plus 36i. A plus bi form, it matches. So that would be our final answer. On the next one, you look back and you say, hey, that looks like two binomials. And that's exactly how you want to work this one. Think of it like binomials, but it's really two complex numbers that need to be multiplied together. But they have real parts and they have imaginary parts. So it's just like your binomials. So with that, we're going to go FOIL, because that's how we used to multiply two binomials. So first times first, which is 5 times 2, or 10. Outsides, 5 times negative 7i would be negative 35i. Insides would be 18i. Last times last, 9i times a negative 7i would be 63i squared. Now again, combine like terms, etc., and simplify wherever possible. So I'm starting to underline. I see some like terms. They both have variables I on them. So you're going to do some addition and subtraction. Look down at the other end. We have an I squared, which we know is equivalent to something. So let's simplify and let's put this all together, trying to put the real part first, the imaginary part second. So down here on the end, 63 I squared is better known as negative 63. And if we have 10 added to a negative 63, we would have a, you know what, I made a sign error there. I think that's supposed to be a negative, because last times last, 9i times 7i is negative 63i squared. So actually, I squared would be negative 1. A negative times a negative would give me a positive 63. That positive 63 with the 10 that's down here, as regular real numbers, would add together, and we would get 73 for our first term or real part. Added to, look at your i's, the imaginary part, a negative 35i plus an 18i definitely leaves us a negative 17i. If you'd like to write 73 minus 17i, that would be the same thing. That would be your final answer. So look at these real carefully. Most of the time when we were adding, we stayed within the complex number system. When we were subtracting, same thing. When we multiplied, we ended up with a complex number. But the question is that always going to happen? So that's a next choice. So look at this combination. It happens to be an imaginary number multiplied by an imaginary number, but they're so close to each other. Take a look. The real parts are the same, but the imaginary parts are just opposites, or we could call these conjugates. So I have two complex conjugates that are multiplied here, and if we do our FOIL thing again, watch what happens. First times first is 1. Outsides, that would be 1 times negative I is negative 1i, or just negative I. Inside times inside would be plus I. Last times last would be negative I squared. We know a negative I squared simplifies to a 1, and we already have a 1 out front, so 1 and 1 would give us a 2. But that negative I and that I cancel out, so our final answer here is a 2. So look real carefully. We started in what we would call the complex number system. We multiplied two conjugates together, and we got a whole number, and this whole number is real. So look carefully. We will be calling any number, any complex number, that is in the form of a plus bi, and its partner that's in the form a minus bi, we will call them complex conjugates. And they are unique in that when you multiply them together, you should always get a real number, a whole number here. So let's look and see what I have underneath. Every real number is complex because you could write any real number in the form of a plus 0I. So if I asked you, how would you write the number 8 as a complex number? You hopefully would be able to tell me 8 is the real part. It does not have a complex part. So 8 plus 0I would be the answer. Now, does that seem like overkill from what we're used to? Well, yeah, but if you're in the complex number system, that's the way we need to write it. Lastly, we need, one more thing here. The combination of complex numbers is called the complex conjugate, which I already threw up there. That was the other missing piece there. So now, why is this important? Because if you think back to that last slide, I added, I subtracted, I multiplied a couple different combinations. Last but not least, we haven't talked about how to divide, and that's all that's left. So here are two examples of division, and the rule is in order to divide with complex numbers, you must get the denominator back into real number form. Well, we just talked about what we would need, and that real number form would have to be something using the conjugate. So that conjugate here, if my denominator is negative 2 minus 5i, that conjugate would have to be the a minus bi form. And since this already is negative, our conjugate would be negative 2 plus 5i. Now, we're going to tell you to go ahead and multiply that on the top as well, because you know in algebra that when you multiply top and bottom by the same thing, you basically have that fancy form of 1. And when you multiply any number by 1, it doesn't change the value. It just helps you get to a new desired result. So let's undo that 1 so we can actually multiply now. And so that form that we're going to use looks like the same thing we did a minute ago. But remember, our goal is to get, and we'll leave an equals up there, a whole number in the denominator. So the very first choice is start thinking of me like complex numbers, binomials. Let's multiply this denominator out, because if you can't get a whole number down there, then something's wrong and you might as well go back to the drawing board, figure it out, find your error, etc. So here we go. Denominator only. First times first should be a 4. Outsides, negative 10i. Insides, positive 10i. Last times last, negative 25i squared. Simplify me. Well, we can see right here that the i's cancel. The 25, negative 25i squared turns into positive 25. With the 4 added together would give us a denominator of 29. That's exactly what we're looking for. And so our denominator is now going to be a 29. Now let's go ahead and multiply the top. You're hopefully noticing that they are not conjugates, so we're probably going to have some things left over there. But we still should be able to do some simplifying. So first times first, negative 8. Outsides, 20i. Insides, negative 2i. Last times last, plus 5i squared. Again, interesting enough, we can simplify that. Let's do the real part first, which would be 5i squared is really negative 5. With the negative 8 out front would give us a negative 13 for the real part. The imaginary numbers, 20i subtract 2i, leaves us a 18i. So we could leave it just like that in fraction form, except for when the directions say write in a plus bi form. If it says, like this one does, write in a plus bi form, then we must separate it. Take that 13 and put it over that 29, that denominator separately, plus the 18i over that same denominator. So now it is separated. The real part would really be the fraction negative 13/29. The imaginary part would be that 18i over 29. All right. The second example we'll leave here. The denominator doesn't look like a complex number. but you still should be good because you need to think of it. What is 5i? 5i is really 0 plus 5i. So its conjugate would be 0 minus 5i. And since we have to multiply by that conjugate, if you don't want to go 0 minus 5i, yes, a negative 5i could be a shorter form. And again, we have to do that on the top and the bottom to simplify this. This one's going to be a little nicer because there's not so much multiplying to do. But here we go. We want to make sure the denominator comes out to be a whole number, a real number first. So 5i times negative 5i is negative 25i squared, better known as 25. Up on top, we have a complex number, 20 plus 15i, times by that negative 5i. So that's sort of like a monomial times a by. So we have to distribute. Here we go. Negative 5i times 20 is negative 100i. 15i times a negative 5i is negative 75i squared. Simplify there, we know I squared is negative 1, so that negative 75 times negative 1 is a positive 75. Put it in the A slot, or the real number slot, and then minus 100i would come next. Keeping it all over 25, that would be fine except for, again, A plus BI form. Now in this case, when you separate it, you're looking that, hey, you have normal, regular fractions, and those fractions can be reduced, unlike our last example where 13 over 29 did not reduce and 18 over 29 did not reduce. This one does. So when we finished, start thinking, okay, 75, 25, there's a whole number, 3 over 1. 25 into 100, again, another nice whole number. But just after you reduce, you still must leave it separated in A plus BI form. So our final answer should be 3 minus 4i. So our final answer, if you want to put that over 1, you can, but it's not necessary. So our complex number, after we divide, is 3 minus 4i. All right, so we have just shown you that in the complex number system that you just learned about, you can add, subtract, multiply, and divide, and that will be a big part of today's work. Keeping in mind that you read about when do you use these imaginary numbers. Obviously, we use them in the quadratic formula is 1, but for those of you who haven't explored it yet, in electronics, when you're trying to build a circuit, parallel circuits, series circuits, you're going to be using negative and imaginary numbers to figure the circuitry. We won't be doing that in class, but that would be an example of where you would use this in real life application. So that's all for now. I think you should be good to start the problems, but bring any questions you may have to class, and we'll try to answer those for you.